Okay, so there was a question about homework 8 and problem 3 and problem 4. Is that correct?
Yes.
So problem 3 says to consider the symmetric group S3. So we know this group has 6 elements, and one element is the cycle 1, 2, 3 in S3. And what is the cyclic subgroup generated by this permutation, sigma? So the cyclic subgroup, in general, any cyclic subgroup, you take an element of the group and you look at all powers of the element, sigma to the I, where I is 0, plus or minus 1, plus or minus 2, all powers of the element. Of course, it looks like it could be infinitely many, but of course, if the group is finite, there are only a finite number of elements. So what are the elements? Let's see, sigma of 0, that's always the identity. That's what raising an element to a group to the 0th power means. Sigma to the first power is just sigma. What is sigma squared? That's sigma times sigma. If you iterate sigma, 1 goes to 3, 3 goes to 2, 2 goes back to 1. So that's sigma squared. It's this permutation. What is sigma cubed? If you replace sigma 3 times, you get back to the identity. So the third power of sigma is the identity. Right? Sigma times sigma squared, which is sigma cubed, is the identity. This also means that the inverse of sigma is sigma squared. So when you're looking at all the powers of sigma, you really just get a set consisting of 3 different permutations. 1, sigma and sigma squared. That is the identity, the 3 cycle 1, 2, 3, and the 3 cycle 1, 3, 2. So this is the cyclic subgroup generated by sigma. Okay. So this is a basic construction in group theory. You have a group, you take any element in the group, X, you look at all the positive and negative powers of X, that forms a subgroup, and it's called the cyclic subgroup generated by X, and it can be finite or it can be infinite, and in this case, it's finite. Any questions about that? By the way, let me remind you, I sent out a note that exam 2 is going to be on Monday, May 10th. So 2 weeks roughly from today. Right. This is part A. What is part B? We want to, so we're calling this cyclic subgroup H. Part B is to prove H is a normal subgroup. So that means you want to prove that XH equals HX for every permutation X in sigma 3. Of course, see, we need some notation for sigma 3. Sigma 3 is a group with 6 elements. And what are they? There's the identity, there's a 3 cycle sigma, and there's a 3 cycle sigma squared. And then we also have 3 transpositions. So let's say tau 1 transposes 2 and 3, tau 2 transposes 1 and 3, and tau 3 transposes 1 and 2. So tau 1, tau 2, tau 3. So these are exactly the 6 elements in the group. Now, H is a subgroup consisting of these 3 elements. So if we take E times H, that's certainly H times E, and multiplying everything in a group by something in the group doesn't change it. So these 3 relations hold when you look at the left coset and the right coset by the elements E, sigma, and sigma squared. What about tau 1? What is tau 1 times H? So that's tau 1 times this subgroup consisting of E, sigma, and sigma squared. So this means take everything in the subgroup and multiply it on the left by tau 1. You get tau 1 times the identity, tau 1 times sigma, and tau 1 times sigma squared. And what is this? You have to compute it. So, well, tau 1 is tau 1. Tau 1 times sigma, that's 2, 3. That's the transposition tau 1. And sigma is 1, 2, 3. And if you compose these two, that is multiply the permutations, 1 goes to 2, 2 goes to 3, so 1 goes to 3. 3 goes to 1. 2 goes to 3, goes back to 2. So tau 1 sigma is 1, 3, which is tau 2. Tau 1 sigma squared, that's 2, 3 times 1, 3, 2. So this sends 1 to 3 and 3 to 2. So 1 ends up at 2. 2 goes to 1, goes to 1. 3 goes to 2, goes to 3. So tau 1 sigma squared is the permutation, is the transposition 1, 2, which is tau 3. So this coset is simply the set of 3 cosets, tau 1, tau 2, tau 3. Now, so what we have is that tau 1 times the coset times the subgroup H consists of tau 1, tau 2, tau 3. And so now we could do a lot of calculations. We can also calculate H tau 1, because these have to be the same. Let me do that calculation. So H is E sigma and sigma squared, and times tau 1. So that's tau 1, sigma tau 1, sigma squared tau 1. We have to calculate. Sigma tau 1, that's the 3 cycle 1, 2, 3 times the transposition 2, 3. Let's see, in this, 1 goes to 1, goes to 3, 3 goes to 2, 2 goes to 3, so 3 goes back to 3. What is it? 1 goes to 1, 1 goes to, this sends 1 to 1, this sends 1 to 2, this sends 2 to 3, and this sends 3 back to 1. So 2 goes to 3 goes to 1, and 3 goes to 2 goes to 3. So this is just the transposition 1, 2, or tau 3. And sigma squared tau 1 is 1, 3, 2, 2, 3. So what is this? 1 goes to 1 goes to 3. 3 goes to 2 goes back to 1. 2 goes to 3 goes to 2. So this is the transposition tau 2. So H tau 1 also consists of tau 1, tau 3, and tau 2. It's the same set. So tau 1H equals H tau 1. And you can also check exactly the same way that tau 2H equals H tau 2, and tau 3H equals H tau 3. And we already had that the right and left cosets were the same when you multiply H on the left and the right by E sigma or sigma squared. So this is a direct proof that H is a normal subgroup of S3. Of course, there's another way to see this, which is if this is the group S3, let's say this is H, it consists of E sigma and sigma squared. What's left is tau 1, tau 2, tau 3. Now, cosets are pairwise disjoint, and they all have the same number of elements. So if this is H, if you take any coset of H, it's either this or it's 3 elements different from these. It has to be this. So whenever you have a subgroup H and the number of cosets is exactly 2, it automatically has to be normal. That is. So if you have a subgroup which is exactly half the group, it's automatically a normal subgroup. But that's a kind of a group theoretical argument, but this is a calculation which shows the same thing. Okay. Any questions about this? This is all the central part of group theory in the first course, and it takes a lot of time to understand. All right. What's the quotient group? Let me do that on just another piece of paper. Well, S3 mod H, this is just a set of left cosets. This is a set that consists of 2 elements. One element is H, that's the subgroup, and the other is any left coset, for example, tau 1H. That is the quotient group, right? And the multiplication table is the following. We have H, tau 1H, H, tau 1H. You multiply them, H times H. So remember, what's the rule for multiplication of cosets? It's always XH, when you have a normal subgroup, XH times YH is XYH. So H times H, that's EH, if you like, times EH. That's E times H, which is E squared H. E is the identity, which is H. H times H is H. EH times tau 1H is E tau 1H or tau 1H. And tau 1H times EH is the same thing, tau 1H. And what is this times this? Tau 1H times tau 1H, that's tau 1 squared H. But tau 1 squared is the identity. This is the identity. So that's the multiplication table for the quotient group. And if you look at this, you see this is abelian. Because for any cosets, XH, YH equals YH, XH. That's just the fact that this is symmetry in the multiplication table. So you can just check every possible multiplication. There are only 4 of them, and it's a billion. Right. End of the problem. Okay. Can I answer any questions about this? I mean, this is exactly what you're going to have to be able to do on the next exam. Okay. Problem 4. In problem 4, we consider the symmetric group S4. This is a much bigger group. What is the order of S4? It's 4 factorial. 1 times 2 times 3 times 4. So this is a group with 24 elements. So there are going to be a lot of things to check. Let's see. Well, in part A, we let sigma be the cycle 1, 2, 3, 4 in S4. And you can calculate what is sigma. So we want to compute the cyclic group H generated by this permutation sigma. So it consists of the powers of sigma. What is sigma squared? It's 1, 2, 3, 4 composed with 1, 2, 3, 4. This sends 1 to 2, 2 to 3, so 1 goes to 3. 3 goes to 4, goes back to 1, so that's a transposition. 2 goes to 3, goes to 4, and 4 goes to 1, goes to 2. So sigma squared is the product of these 2 transpositions. What is sigma cubed? Well, that's sigma times sigma squared. So that's 1, 2, 3, 4 times 1, 3, 2, 4. What is that? Let's see. 1 goes to 1, 1 goes to 3, 3 goes to 4. 4 goes to 2, to 2, to 3. 3 goes to 3, to 1, to 2. 2 goes to 4, goes back to 1. So sigma cubed is 1432. And what is sigma to the 4th power? Well, let's say that's sigma squared, sigma squared. That's 1324, 1324. Disjoint cycles commute, so I can write that as 1313, 24, 24. That's the identity times the identity. That's the identity. So sigma to the 4th is the identity. So H is a subgroup consisting of exactly 4 permutations: E, sigma, sigma squared, and sigma cubed. All right. Any questions about this? All right. So in part B, we want to compute 2 cosets. The coset, the left coset 1, 3H. So that's 1, 3 times each of these permutations: E, sigma, sigma squared, and sigma cubed. When you multiply each of these by 1, 3, you get 1, 3. 1, 3 times sigma, 1, 3 sigma squared, and 1, 3 sigma cubed. And what are these? Well, we have to compute it. What is 1, 3 sigma? So that's the permutation 1, 3 multiplied by sigma, which is 1, 2, 3, 4. Let's see. This sends 1 to 2 to 2, 2 to 3, and 3 goes back to 1. 3 goes to 4, and 4 goes to 3. So 1, 3 sigma is 1, 2, 3, 4. What is 1, 3 sigma squared? So that's 1, 3. And what was sigma squared? 1, 3, 2, 4. 1, 3 times 1, 3 is the identity, so that's just 2, 4. And what is 1, 3 sigma cubed? That's the permutation 1, 3 times the 4 cycle 1, 4, 3, 2. And just so I don't have all the fun, why don't you calculate this? What is this permutation? All right, so spend a minute or two to do the calculation. When you multiply these permutations, where does 1 get mapped to? Where does 1 get sent? So can someone tell me?
4.
Yep. 1 goes to 4, 4 goes to 4, so 1 goes to 4. Where does 4 go?
4 goes to 1.
Right. 4 goes to 3, 3 goes to 1, so 4 goes back to 1. Where does 2 go?
2 goes to 3.
Yep. And where does 3 go?
3 goes to 2.
Right. So this is the product of the transpositions 1, 4, and 2, 3. So what we have is when you take sigma, the cycle 1, 2, 3, 4 in S4, and if H is the subgroup generated by sigma, that consists of the identity, sigma, sigma squared, and sigma cubed. And when we calculated the left coset 1, 3, that transposition times H, we got the following. 1, 3 times the identity is 1, 3. And we also got 1, 2, 3, 4. And we got 2, 4. And we got 1, 4, 2, 3. So that's the left coset. And now we have to calculate the right coset. So what's going to be in the right coset? So you multiply every element of H on the right by 1, 3. So that's E times 1, 3. 1, 2, 3, 4 times 1, 3. And 1, 3, 2, 4 times 1, 3. So E times 1, 3 is just 1, 3. These are disjoint cycles. They commute. 1, 3 times 1, 3 is the identity. So this just gives 2, 4. What about these two? Let's calculate them. 1, 2, 3, 4 times 1, 3. This sends 1 to 3 to 4, so 1 goes to 4, and then 4 goes back to 1. 2 goes to 3, 3 goes to 1, goes back to 2. So 1, 2, 3, 4 times 1, 3 is 1, 4, 2, 3. And let's see, this is 1, 3. Oh, I left one out, I think. So H times 1, 3, it's E times 1, 3, 1, 2, 3, 4 times 1, 3, 1, 3, 2, 4 times 1, 3, and 1, 4, 3, 2 times 1, 3. So I have to calculate that. 1, 4, 3, 2 times 1, 3. 1 goes to 3 goes to 2. 2 goes back to 1. 3 goes to 1 goes to 4. 4 goes to 4 goes to 3. So this is 1, 2, 3, 4. So the left coset consists of 1, 3, 2, 4 and 1, 2, 3, 4, 1, 4, 2, 3. Oh, wow, that's interesting. Turns out that that's exactly the same as this right coset. 1, 3, 2, 4, 1, 2, 3, 4, 1, 4, 2, 3. So that's just an interesting calculation. But that's what we had to do for part B. What about part C? So is H a normal subgroup of S4? So that means yes, if and only if every left coset equals the corresponding right coset for all X in the group S4. And we know if we take H and multiply it by any element of itself, that still is H. If we take H and multiply it by this transposition, this condition also holds. Let's see. Maybe we should just do an experiment and pick either a 3-cycle or a let's just do an experiment. I mean, this has to be true for all X. If we're lucky, it's not true for all X, and we'll find a counterexample to this, and then we'll be done. So we'll do the following experiment. Suppose we let, for example, X be the 3-cycle 1, 2, 3. Let's see what happens. So XH is 1, 2, 3 times E 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 3, 2. So we have to calculate each of these. So we have 4 elements. 1, 2, 3 times the identity. 1, 2, 3 times 1, 2, 3, 4. 1, 2, 3 times 1, 3, 2, 4. And 1, 2, 3 times 1, 4, 3, 2. So we need to compute these guys. So, of course, when you multiply a permutation by the identity, it's just the same permutation. What about 1, 2, 3 times 1, 2, 3, 4? So you should try to calculate all three of these, and then I'll do it, and because you have to be able to do this basic multiplication. For example, this sends 1 to 2 to 3, 3 to 4, 4 to 1 to 2, and 2 to 3 to 1. So this is the cycle 1, 3, 4, 2. This sends 1 to 3 back to 1, 2 to 4, 4 to 2 to 3, 3 to 1 to 2. So this is the 3 cycle, 2, 4, 3. Right? 1 goes to 1 to 3 back to 1. 2 goes to 4 to 4 to 4. 4 goes to 2 to 2 to 3. 3 goes to 1 goes to 2. So that's this 3 cycle. And 1, 2, 3, 1, 4, 3, 2. 1 goes to 4, goes to 4. 4 goes to 3, goes back to 1. 3 goes to 2, goes to 3. And 2 goes to 1, goes to 2. So this is just this transposition 1, 4. So these are the 4 elements in the left coset. Let's compute the right coset, see what we get. What is XH? So this is the elements, the subgroup H, 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 3, 2, times X. So it consists of the elements E times 1, 2, 3, 1, 2, 3, 4 times 1, 2, 3, 1, 3, 2, 4 times 1, 2, 3, and 1, 4, 3, 2 times 1, 2, 3. Of course, the identity times anything is the anything, so this is just 1, 2, 3. What is the product of these two permutations? 1 goes to 2, goes to 3. 3 goes to 1, goes to 4. 4 goes to 4, goes back to 1. 2 goes to 3, goes to 2. So this is just 1, 2, 3, and this is 1, 3, 4. This 1 goes to 2, goes to 4. 4 goes to 4, goes to 2. 2 goes to 3, goes back to 1. 3 goes to 1, goes to 3. So this is just a 3 cycle, 1, 4, 2. And 1, 4, 3, 2 followed by 1, 2, 3. 1 goes to 2, goes back to 1. 2 goes to 3, goes to 2. 3 goes to 1, goes to 4. 4 goes to 3. So this is just the transposition 3, 4. So these are the 4 permutations in HX in the right coset. And if you look, this set of 4 things is different from this set of 4 things. Let's see, let me just double check this. 1 goes to 2 goes to 3, 3 goes to 1 goes to 2, 2 goes to 3 goes to 4, and 4 goes to 1. Yeah, this is a 4 cycle. But in any case, they're different. So this is the important point. For this particular permutation 1, 2, 3, the left coset 1, 2, 3H is different from the right coset H times 1, 2, 3. So H is not a normal subgroup. Okay. Any questions about any of this? I mean, this is doing some group theory. So we talked about quotient groups, and we talked about homomorphisms, and a little bit on Monday, we saw a connection between normal subgroups and homomorphisms. So let's just recall the definition of a homomorphism. Suppose we have G and G prime groups and a function f from G to G prime. And this function is called a homomorphism if it satisfies the property that f of x times y is f of x times f of y for all elements x and y in the group. So as a kind of a picture of that, perhaps we have, if this is the group G and this is G prime, we have x that gets sent to an element f of x, and y gets sent to an element f of y. And then over in G prime, I can multiply these two elements and I get f of x times f of y. On the other hand, in G, I could multiply x and y and get the element xy, and xy gets sent to an element f of xy. And you have a homomorphism if whether you map the elements to G prime and then multiply, or multiply in G and then map to G prime, you get the same element. That's what this equation says. And we say that a homomorphism F from G to G prime is what is called an isomorphism. If F is 1 to 1, and on 2. Let's see. What's an example of a homomorphism? Suppose I take G and G prime just to be the integers under addition. So these are additive groups. For additive groups, this condition, so if G and G prime are additive, multiplication is replaced by addition. So the definition of a homomorphism would be f of x plus y equals f of x plus f of y. So define the function f from z to z by, let's say, f of x is 7 times x. I claim this is a homomorphism. Why? Because for any integers x and y, f of x plus y is 7 times x plus y, which is 7x plus 7y. And 7x is f of x, and 7y is f of y. So this condition is satisfied. So this is an example of a homomorphism. Let's take another example. Suppose I let G and G prime be equal to the infinite cyclic group generated by some element A. So this means G consists of all powers of A. There's the identity, A squared, A cubed, A to the fourth, going on forever. And also A inverse, A minus 2, A minus 3, and so forth, going on forever. That's the infinite cyclic group. And the multiplication is A to the I times A to the J is A to the I plus J. Suppose we define a function f from the cyclic group to itself by f of a to the power I is a to the power 7 times I. So this defines a function. And the question is it a homomorphism? So suppose we take x equal to a to the I and y equal to a to the j, right? Because any element is a power of a. So f of x, y, that's f of a to the I times a to the j. But a to the I times a to the j is a to the I plus j. And f of a raised to a power is a raised to 7 times that power. But of course, 7 times I plus j is 7i plus 7j, which is a to the 7i times a to the 7j. And this is f of a to the I, and this is f of a to the j, and this is x and this is y, f of x times f of y. Right? So take a look at that for a moment, and let's look at one other example. Suppose we take G to be GL2R. this means the set of all 2 by 2 matrices, A, B, C, D, with determinant AD minus BC not equal to 0. So this is the determinant of the matrix X. And suppose we let G prime be the multiplicative group of non-zero real numbers, right? Because if you have two non-zero numbers, you multiply them, it's non-zero, that's a multiplicative group. So consider the function, the determinant, which sends every matrix in GL2I, let's call this F, sends a matrix to a non-zero real number where F of X is the determinant of X. Is F a homomorphism? Right. So spend a minute or two to understand this example of a homomorphism and decide whether or not the determinant is a homomorphism. Right? So yeah, spend a minute or two just to think about that. Any questions about this? So the determinant is a homomorphism, and that's what we had proven when we were studying matrix groups. If you have X equals A, B, C, D, the determinant of X is AD minus BC. And this is multiplicative. The determinant of XY is the determinant of X times the determinant of Y. So the determinant function from GL2R, these are 2 by 2 matrices with non-zero determinant, to the multiplicative group of real numbers is a homomorphism. Right? It is a homomorphism. Let's look at some properties of homomorphisms. So we have a homomorphism F from G to G prime. So the first property is if you take the identity E in F, F of E is E prime. Right? So this is G prime. Here's this function between them. Here's the identity in E. Let's say E prime is the identity in E prime. F sends E to E prime. And the proof goes as follows. We know that E is equal to E times E. So F of E, that's F of E times E. But because F's a homomorphism, this is F of E times F of E. Now, I don't know yet what F of E is, but it's an element of the group. So I multiply by F of E inverse. So I get F of E times F of E inverse is F of E times F of E times F of E inverse. And by associativity, this is F of E times F of E inverse. This is the identity, an element times its inverse, which is f of e. And here, f of e times f of e inverse, of course, is the identity. So what I have is e prime equals f of e. End of proof. What's another property of a homomorphism? So we have f from G to G prime a homomorphism, and then the element x in G. So for all x in G, f of x, that's over in G prime, you can take the inverse there. On the other hand, you can also take the inverse of x in G and apply f to that, and we get the same element. So you can give a kind of a diagram to show what's going on. So over in, this is G and this is G prime, I have x, it goes to f of x, and that goes to f of x inverse over in here. On the other hand, x in G, we have x inverse, and then we can take f of x inverse. And we're told we get the same element. So you get from here to here either by going across and down or down and across. That's just a picture of what this statement means. And how do we prove this? A statement needs a proof. You can't just believe it's true. You have to prove stuff in mathematics. So we know that the identity is x times x inverse. So f of e is f of x times x inverse. Of course, f of e is the identity in G prime, it's E prime. And by the property of being a homomorphism, this is f of x times f of x inverse. So f of x times this element is the identity. That means f of x inverse is the inverse of f of x. And that's the whole proof. Now, again, this is just repeating what we did on Monday. This is G and this is G prime, and I have this function f from one to the other. I know the identity gets mapped to E prime, but it could be that there's other stuff that gets mapped to E prime. It could be that there's a whole set of elements in G, and they all get mapped to E prime. And that set of elements is called the kernel. So the kernel of a homomorphism F, it's the set, I'll just write kernel of F, or sometimes I just write KER of F. This is the set of all X in G, such that f of x is the identity in G prime. It's everything, all this green stuff, everything that gets mapped to E prime. And so, for example, we know f of E is equal to E prime. So E is always in the kernel of a homomorphism, but other things can be there as well. And a very important fact is the following. So we have F from G to G prime, a homomorphism of the group G into the group G prime. The kernel of F is always a normal subgroup of G. So we'll prove this in two steps. First, we need to show kernel of F is a subgroup. And then we'll show that kernel of F is a normal subgroup. So why are these statements true? How can we prove this? So proof of one. First of all, what does it mean to be a subgroup? A subset of a group is a subgroup if it contains the identity, if it's closed under multiplication, and if it contains the inverse of each of its elements. So we know, because we already proved, that the identity of G is in the kernel of F. Now, suppose we take any two elements in the kernel of F. We want to show xy is in the kernel of F. Well, why is that? So f of x times y, but this is f of x times f of y. And because x and y are in the kernel, f of x equals the identity, and f of y equals the identity. So this is identity times identity, which is identity. So the f of xy is the identity. So the product xy is in the kernel of F. And finally, if x is in the kernel of F, then f of x inverse, which I proved is f of x, the inverse of f of x, but x is in the kernel, so f of x is the identity, and the inverse of the identity is the identity. So x inverse is in the kernel of F. So the kernel of a homomorphism contains the identity, it's closed under multiplication, contains the inverse of each of its elements. So therefore, kernel of F is a subgroup. And now we want to show that this subgroup is normal. So we must show that if x is in the kernel of F, then AX A inverse is in the kernel of F for all elements of the group. So what can we say about f of AX A inverse? That's f of A times f of x times f of A inverse. That's f of A. F of x is the identity, and f of A inverse is the inverse of f of A. So this is f of A times f of A inverse. That's the identity. And we're done. So AX A inverse has to be in the kernel. So whenever you have a whenever you have a homomorphism, the kernel always is a normal subgroup. Now, there are other subgroups associated with the homomorphism, and let me show some of them. So we have F from G to G prime. What is called the image of F is everything y in G prime such that y equals f of x for some x in G. So here's the picture. Here's G and G prime. You take x, it goes to some element f of x. And every element in G gets mapped to something over here. But of course, so you look at all of these images, that's some subset of G prime. So this is what is called the image of F. It's just everything in G prime which comes from something in G. It's everything which is of the form f of x for x in G. So for example, we had seen before the homomorphism from Z to Z given by f of x equals 7 times x. So here's Z, here's Z, here's this homomorphism. What is the image of F? Well, it's the set of all multiples of 7. 0 plus or minus 7 plus or minus 14 plus or minus 21 and so forth. So sitting over here in x, you have a part of x, 0 plus or minus 7 plus or minus 14 and so forth. That's the image of F, the set of multiples of F. What's not in the image of F? Everything over here, like 1, 2, 3, 4, 5, 6, 8, 9, right? Any number that's not divisible by 7 is not in the image of F. So the image of F is a subset, and usually a proper subset of what's of the group on the right-hand side. And there's a nice statement, a theorem if you like, which says that when you have a homomorphism, from G to G prime, the image of the homomorphism F is a subgroup, generally not a normal subgroup, but is a subgroup of G prime. So how does the proof of that statement go? Well, we have F from G to G prime. F of the identity is the identity. So the identity is in the image of F, because the identity in G gets mapped to the identity in F, so this is in the image of F. And suppose Y and Y prime are in the image of F. Then there exist elements x and x prime in G with f of x equal y, f of x prime equals y prime. So y prime, that's f of x times f of x prime, but that's f of x, x prime. So there's an element in G that f sends to y prime. So the image of F is closed under multiplication. And also, if y is in the image of F, y inverse, and y is equal to f of x, y inverse is f of x inverse, but we saw that f of x inverse is f of the inverse of x. So this is an element of G. So this is in the image. So this argument shows that the image of a homomorphism is always a subgroup of the range space. Again, all of this is in the notes, written out legibly and neatly, and it's very convenient. Are there questions about this? So we showed that the kernel of a homomorphism is a normal subgroup. And the converse is also true. Every normal subgroup is the kernel of a homomorphism. Proof. Well, so let N be a normal subgroup of the group G. So we have the quotient group G mod N, the set of all left cosets. And define a function, I'll call it pi, from G to G mod N by pi of x is the left coset xn. I claim this is a homomorphism. So for all x and y in the group G, pi of x times y is the coset xy n. But that's the product of the cosets xn and yn. And that's pi of x times pi of y. So therefore, pi is a homomorphism. And what's the kernel of pi? So an element x is in the kernel if and only if pi of x equals the identity. What is the identity in G mod n? It's the coset en, or n. So if and only if pi of x is en. But pi of x is xn, so if and only if xn is equal to en, or n. And this is true if and only if x is in n. If x is in n, this is a subgroup xn equals n. And conversely, if xn equals n, then x times e, which is x, is in n. So therefore, the kernel of pi is n. So every normal subgroup is the kernel of some homomorphism, and pi is called the canonical homomorphism. Right. So the special kind of homomorphisms that are one-to-one and onto are called isomorphisms. So that's a homomorphism that is one-to-one and onto. One-to-one means that if you take two elements, x and x prime, so you have this function f from g to g prime, so x goes to f of x and x prime goes to f of x prime. One-to-one means that whenever x is different from x prime, then their images, f of x and f of x prime, are different. And onto means that for any y in g prime, there exists an x in g with f of x equal to y. So in other words, the image of f is all of g prime. Right? This gets mapped onto the whole group g prime. And whenever you have a function that's one-to-one and onto, every one-to-one and onto function has an inverse function. Because, so here we have f from g to g prime. If I take any element y, if the function is onto, there's always some x that gets mapped to y. So f onto, so let y be an element of g prime. If f is onto, then there is an x in g with f of x equal y. And f one-to-one means x is unique. If you have a different element in g, it can't get set to y, it goes to something else. So for every y, there's only one element x in g such that f of x equals y, and we define the inverse function, f inverse of y, to be equal to that unique element x such that f of x equals y. So if f from G to G prime is an isomorphism, then there always exists a function f inverse from G prime back to G there exists an inverse. And I claim that f inverse is an isomorphism also. So whenever you have an isomorphism from one group to another, the inverse function from G prime back to G is also an isomorphism. So the proof, well, first of all, x always goes to f of x, which is some y in G prime. So f inverse of y is equal to x. So f inverse is onto, right? For any element x in G, f inverse sends f of x back to x. So f inverse is onto. And if inverse of y equals f inverse of y prime, that means that, so what is f inverse of y? That's the element of x such that f of f inverse of y equals y. And f inverse of y prime is the element of x such that f of f inverse of y prime equals y prime. And if f inverse of y equals f inverse of y prime, when you apply f to that, you get the same element. So y equals y prime. So therefore, f inverse is also 1-to-1. Again, it's easy for me to say this and write it down, and it's 100% correct. But it really takes a lot of time at home thinking about this to make you understand the argument precisely. The more interesting part is to show that f inverse is a homomorphism. Show f inverse is a homomorphism from G prime to G. So suppose we let y and y prime be two elements of G prime, and we let x be f inverse of y, and x prime be f inverse of y prime. So that means that f of x equals y, f of x prime equals y prime. So f of x prime is f of x prime is f of y prime. Sorry, f of x prime. Sorry, f of x is y prime. So f inverse of y prime is f of x times f of x prime. Sorry, let me say this correctly. F inverse of y prime is x prime. And x is f inverse of y, and x prime is f inverse of y prime. And this is the definition of a homomorphism. So this proves that f inverse is a homomorphism. So this is really an important fact. So if f from G to G prime is an isomorphism, then f inverse from G prime back to G is also an isomorphism. And let's define a relation on groups. We say G, we say it's isomorphic to G prime if there exists an isomorphism F from G to G prime. And I claim this is an equivalence relation. First of all, the identity function from a group to itself, defined by f of x equals x, is an isomorphism. It's a homomorphism. It's one-to-one and onto. So isomorphism is reflexive. Every group is isomorphic to itself. Isomorphism is symmetric, because if G is isomorphic to G prime, that means you have an isomorphism F from G to G prime. But then we saw that F inverse from G prime to G is an isomorphism. So G prime is isomorphic to G. So if G is isomorphic to G prime is isomorphic to G, that means that this relationship on groups of being isomorphic is symmetric. And finally, isomorphism is transitive. So suppose G is isomorphic to G prime and G prime is isomorphic to G double prime. So you have an isomorphism from G to G prime. You have an isomorphism from G prime to G double prime. So compose them. Just composition of functions, just like you did in calculus. You have from G going to G prime to G double prime. This composite function is f prime composed with f. And you can check that the composition of one-to-one functions is one-to-one, and the composition of onto functions is onto, and the composition of homomorphisms is homomorphism, is a homomorphism. So this relationship of being an isomorphism is transitive, and so we now have an equivalence relation on all groups. So we can talk about isomorphic groups and isomorphism classes of groups. And basically, groups that are isomorphic are the same. It's just like you've sort of changed the name or written them differently, but they're the same group. And okay. So the things we talked about today are really all, again, everything we're doing is sort of fundamental in mathematics and in algebra. You have groups, normal subgroups, quotient groups, cyclic groups, homomorphisms. The kernel of a homomorphism is a normal subgroup. The image of a homomorphism is a group, not necessarily normal. Every normal subgroup is the kernel of some homomorphism. It's always the kernel of what is called the canonical homomorphism. And we have this notion of isomorphism that is a kind of equivalence relation on the set of all the groups in the universe, of which there are many, many, many. Okay. Questions about this? I should say, when you're studying for the exam, one excellent thing to study are all these homework sets, because the homework sets give you show you kinds of problems that you're expected to be able to solve. I mean, not just those, of course, but certainly you need to be able to do all the homework problems in order to do okay on the exam. All right. Well, no questions? If no questions, we will stop for the day. It's supposed to be a beautiful day.
Professor?
Yeah.
Question. If I want to set up an appointment with you, other than the days that we meet up for class for an office hours, I can just send you an email and
Yes.
we can just talk about the available days.
Absolutely.
Okay, thank you.
Yeah. And I'm available unless I'm teaching. I'm always available basically. So it's easy to set up a time.
Gotcha. Thank you.
Sure. All right, anything else? Okay. All right, everyone. Be well. Back on Monday. Enjoy the weekend.